In this video, I'm going to look at the binary coded decimal, which is a method of representing numbers using binary, whereby each group of 4 bits, a nibble, represents an integer. And this can be used for example, when you want to display time, whereby where you've got one number character making up the time display, digital time display, and also in financial data recording and indeed calculations. The binary number system doesn't give us enough accuracy to allow us to do these calculations correctly, so we use the binary coded decimal. So what is the binary coded decimal? It's just a way of representing an integer using 4 bits, or a nibble. So with 4 bits we can represent our integers from 0 through to 9. Okay, and the 4 bits will give us enough, we can go up to 15, so we've got plenty there. So, for example, if I wanted to represent the number 19, I could do so as such, 1, 0, 0, 1. Okay, and if you remember from previous lessons in binary numbers, converting between binary and denary, the numbers, the bits represent from the least significant bit to the most significant bit, 1, 2, 4, and 8. So we can see here that we've got just 1, so that translates to being our 1. And here we have 1, no 2s, no 4s, 1, 8, 8 plus 1 gives us 9. And so this represents 9, and we're representing those together, we've got the number 19. Okay, now there are 2 approaches to representing numbers using the binary coded decimal, and it's just down to the number of bits we use. So in this example, we've got, let's just get that so we can see that better. We've got 2 ways of representing this number, 8,503, using the binary coded decimal number system, or binary coded decimal representation. Okay, the first one we're using 1 byte per digit, per number. So we can see here we've got 1, 0, 0, 0, 8, no 4s, no 2s, no 1s. Here we've got 5 represented in binary. We've got 0, and we've got 3. 1 plus 2 is 3. Okay. This is a little bit inefficient because we've always got these 4 leading zeros, and so we can combine 2 numbers in the same byte. So in this one, for example, we take the first 4 bits. Okay. To represent our first, I need to recalibrate this. Our first 4 bits here, which is 1, 0, 0, 0, which we know is 8. We've got our second group of 4 here, which is 0, 1, 0, 1, which we know is 5. And here we've got our first group of 4 bits, 0, and 0, 0, 0, 0, which we know is 0. And then our last group, 0, 0, 1, 1, which we know is 3. So we've got the number 8, 5, 0, 3. And so that's one way, 2 ways of representing numbers using binary coded decimal. Okay, now I want to go on to just talk briefly about the use of binary coded decimal for financial data. And one of the problems that we've got with the binary number system, particularly representing real numbers, is a lack of accuracy. And it's very difficult to represent real numbers with the type of accuracy that we need, the type of precision that we need for finance. And I'm sure you'd be delighted if your bank, every time you had 33 pence in a transaction, they rounded that down. to the nearest whole number. Very quickly that would become a significant loss to you. So when we represent numbers, real numbers, and accuracy is important, precision is important, then the binary coded decimal offers us a solution. We do have a small problem with this though, okay, and it's when we start adding numbers. So if we take the example of 26 cents and 85 cents, okay, so 0.26, 0.85. Okay, now if we work out the binary coded representation of that, well, 26 we'd have 0, 0, 1, 0, and 6 would be 0, 1, 1, 0. Okay, and 85 we would have 1, 0, 0, 0, and 1, 0. Sorry, I got that wrong. 0, 1, 0, 1. Okay, now if we were to add these numbers together using binary addition, we would get the following result. 0 plus a 1, we get a 1. 1 plus a 0, we get a 1. 1 plus a 1, we get a 0, and we carry that 1. Okay, and 0, 0, and we get that 1 there. And when we go through 0, 1, 0, 1. Okay, and that's our result. Now, the problem with that, of course, is that we've got 10 and 11 represented here, which would translate as 0.1011, which just it doesn't make sense. Okay, and so we need to find a way around this. So what happens is, just erase this. If we've got a computer that's recognizing that there is this overflow error, it will make a few quick adjustments, and we will add to this first nibble 6 in binary equals. Okay, which will give us the result 1, 1, 1. Done that right? I haven't done that right. Let me go back. It will give us 1, 0, 1, which will give us 0 and carry 1, 0 and carry 1. Okay. We do the same process to the second nibble. Okay, so we would add 6 plus this carry bit, so we would have 0, 1, 1, 1. Okay, which we would add to the result from the previous addition. Okay, so we would get, and I will carry this down. No, I'll do the addition first. So we go 0, 1, 1, 1, 1, 0. Carry that across. 1, 1 is 0. Carry that across. 1, 1 is 0. And we carry that 1. Okay, and we bring this number down, this result from the previous calculation down. 0, 0, 0, 1. When we add those leading zeros. So now we have a binary number that is 0, 0, 0, 1. 0.0001, 0001, 1, 1, 1. Okay, which, if my arithmetic is correct, 0.26 plus 0.85 will indeed equal 1.11 pounds, euros, dollars, whatever you're working with. Okay, so we can get around the problem of binary addition not being quite so cooperative as we'd like when we're using a binary coded decimal system, simply by adding that adjustment nibble to each of the results from the original addition. Okay, now so as I say, the binary coded decimal, it's a little bit clumsy, but it works, and it is used, so we're representing, when we want to represent individual numbers, such as with digital time displays or numeric calculations. I hope that's been useful.